Thank you for your attention. My name is Stephan Cevallos, and I'm from the Neural Engineering and Vision Laboratory. I'd like to discuss my research for the past year, which has been on the design and fabrication of a 3D synchronously updated stimulus source for retinal electrodiagnostic testing. So, ERGs, what are they? It's a category of tests used where we have patients sit in front of a stimulus source, and then we measure the electrical response of the retina to that stimulus source, either by placing an electrode on the sclera or around the eye socket. There's different types of ERGs, and there's full field, multifocal, flicker, peripheral pattern, photopic negative response, sectoral photopic negative response, and visual field, which isn't an ERG, but relevant to this research. As mentioned before, the big difference between the ERGs is the stimulus source, and that determines what they're measuring. Generally, they look something like this: a dome that flashes lights. The multifocal uses a computer monitor. Peripheral pattern uses a dome that extends beyond 180 degrees to stimulate the periphery, but generally a dome. But you have to have a specific device, multiple devices, to run the same category of testing. So at the Neural Engineering and Vision Laboratory, for the past couple years, the goal has been to design one stimulus source that can perform all the ERGs I mentioned before, including visual field testing. This device is quite complex though. There's a lot of parts put together, and on one end we have our patient sit in the open end. It's a dome about 40 centimeters, and each check, I think that's what these squares are called internally, provides a various type of stimulation: colors, luminance, etc. But it's quite complex to manufacture. There's a lot of parts involved with this and a lot of materials: aluminum, Delrin, diffusers, and it's just a lot to put together. So that's what the goal has been in my research. So in spring of 2022, the specific aim was to design a more modular, easier to manufacture dome. And the result was to start thinking instead of squares, inside pentagons. Additionally, we want to reduce our coefficient of variance and luminance. Because we're stimulating the eyes, we want to make sure that our stimulus source is as even and consistent throughout every check and within the check itself. So, hexagons, making a dome of hexagonal prism that tessellate with pentagons, allows each check to be the same size, uniform throughout the entire stimulus source, and reduces our part count because each hex has the diffusers built in. They're 3D printed in one piece, and this is what the experimental setup looks like. On one end, the diffuser check candidate, because it's all contained in one piece, and the other, a cell phone. Using this 200 megapixel sensor to take a 50 megapixel raw image captures enough data. So their images are transferred automatically to MATLAB and ImageJ for image analysis. Here's what it looks like. As you see, this is not perfect. It's not good, but it does prove ultimately that the hexagons do tessellate with pentagons to form a dome of a similar radius. But to improve this, that's what the goal of the research was in fall of 2022. This is the new hexagon prototype. It has different stops so diffusers can be inserted at different lengths, and it improves testing efficiency quite dramatically. Additionally, diffusers can be 3D printed in different methods using the same materials, but it allows just a broader range of experimentation. Here's what the diffuser candidates look like. They're similar from the outside, but their internal geometries are quite complex. But ultimately, this is what it looks like put together with one diffuser. Well, ultimately, what does it mean? It means this is the result. Much better than before. This is our analysis from ImageJ. This is before, after, big improvement. But what does it mean? What does all this work mean in 3D printing these diffusers? It means a coefficient of variance of 7.5%. The ISO standard is 3%, the goal right now is 5%, but from before, coefficient of variance is 18%, and a range of coefficient of variances in the previous generation, this should be a consistent 7.5%. So it shows that this is moving in the right direction, that it indicates that 3D printing can still be viable for printing these optic diffusers, and it shows that building this dome doesn't have to be so time consuming because it could just be 3D printed and glued together. So with that, I want to thank all my friends and people who have contributed: Ali, Alex, Connor, Karina, Marty, Samson for providing technology, the university, the College of Engineering, the College of Medicine, the Richard Lowenthal Department of Bioengineering, the Makerspace, the Neural Engineering and Vision Laboratory. First and foremost, but cannot say nothing to Dr.
And with that, I will take questions.